Welcome, everybody. It's my pleasure to introduce today Oliver Vipond from Oxford University, and he'll be telling us about local equivalence of metrics for multi-parameter persistence modules. Thanks, Oliver.
Thanks, Henry. Thanks, Henry, for the invite to speak at this online seminar. Just a little bit about myself. I'm a third-year PhD student at the University of Oxford, working in applied topology, and I'm supervised by Ulrika Tillman and Vidit Nanda. And I'd like to thank my funding body, EPSRC, for supporting me and my research throughout my PhD studies. Today I'm going to be talking about metrics on multi-parameter persistence modules. But to start with, I just wanted to recap the topological data analysis pipeline and the kind of one-parameter paradigm and the multi-parameter paradigm. So I hope to most people listening, the one-parameter persistence pipeline is fairly familiar. So the idea is that we start with a data set, which we're going to model as a topological space equipped with some filter function f. So we can think of our space being some kind of point cloud embedded in Euclidean space, if you like. And then from this set of data, we induce a filtration of topological spaces, a sequence of spaces. So for example, here I've illustrated the sublevel sets associated to the distance function of this point cloud. Then if we hit this filtered collection of topological spaces with a homology functor with coefficients in a field, we give rise to an object called a persistence module. Now, a key aspect of single parameter persistence is that we know that all of these single parameter persistence modules have this decomposition as a series of bars, and this is known as the bar code of a one-parameter persistence module. And if we have lots of data sets and lots of persistence modules, we might want to analyze their differences and compare them with metrics. The multi-parameter setup is very similar, apart from it allows a bit more flexibility. So here we model data rather than just a scalar-valued function, we model it as a topological space together with a multi-parameter function. And these multi-parameter functions can be useful because in real-world data, we tend to be more noisy than these kind of idealized examples that I've sketched out in this one-parameter setup. So for example, here I've sketched data which looks like it's lying on a ring, but there's a number of outliers, and so it might be hard to detect this ring if we just use ordinary single-parameter persistence. So given a multi-parameter function, completely analogously to this single parameter filtration, we give rise to something called a multi-filtration, where rather than just varying one parameter, we can vary multiple parameters and create a whole family of topological spaces. Again, if we hit this filtration of topological spaces with a homology functor with coefficients in a field, we give rise to what's known as a multi-parameter persistence module. And if you know anything about multi-parameter persistence, you probably know that in this setting, we don't have the same decomposition theorem that we had in the single parameter setup. So our objects here are a lot more complicated than in the single parameter setup, and we don't have this nice decomposition into barcodes. But nevertheless, we might like to do some analysis on these objects, and so today I'm going to be talking about metrics on these multi-parameter persistence modules, and that's really motivated by analyzing these complicated objects that arise from multi-filtered data sets. So you may all be familiar in the one-parameter setup with two different distances on single parameter persistence modules. An algebraic kind of distance known as the interleaving distance, where if you have a module M and a module N, you look for morphisms between the modules which kind of knit these two modules together. And the closer that you can knit these two modules together, the closer you say they are in the interleaving distance. And just from its description, this distance seems quite hard to compute because you're looking for these complicated morphisms between these complicated objects. And we also have a more kind of combinatorial distance known as the bottleneck distance, where if you look at the barcode decomposition of these modules, you look for a matching between these barcodes. And this distance seems a lot easier to compute because our objects are a lot more simple and we have efficient algorithms to compute this style of matching distance. So in the single parameter case, we have this nice theorem known as the isometry theorem, which says In fact, these two distances, which a priori seem different, are in fact the same distances. And so we can compute this interleaving distance or this bottleneck distance, and the result is the same. And we will see that this is quite different in the multi-parameter setup. There's an analogous interleaving distance and a distance which is similar to the bottleneck distance, but in this situation, they're not isometric, they're not the same. And so in the single parameter case, this bottleneck distance is really relying on this barcode decomposition, and that's why this bottleneck distance doesn't really naturally generalize to multi-parameter persistence modules so easily. So in the multi-parameter setup, again, we can also define this complicated algebraic distance known as the interleaving distance. And we can also define an analog to the bottleneck distance, which I'm going to call the matching distance, which looks at barcodes contained in our multi-parameter module. But in this situation, we don't have the isometry theorem. Rather, we just have stability. We just know that the interleaving distance bounds the matching distance. So the question I want to ask in this work is, whilst we don't have this isometry theorem, perhaps we can sandwich this matching distance in between two expressions involving the interleaving distance. So we want to know, although the matching distance is bounded by the interleaving distance, can we bound the interleaving distance by the matching distance? And we answer this question in the positive. Yes, we can bound the interleaving distance by some multiple of the matching distance, but this inequality will only hold locally. It's not globally true. So to start with, because multi-parameter persistence might not be familiar to some people listening, I'm going to try and introduce multi-parameter persistence in an intuitive way. So one of the first main differences between single parameter persistence and multi-parameter persistence is that rather than working with a totally ordered set R, as in single parameter persistence, we're working now with a partially ordered set. And the partial order we're going to consider on R to the n is going to be the coordinate-wise partial order, where we say two elements of R to the n, A is less than or equal to B, if and only if it is less than, A is less than B coordinate-wise. And this kind of is the root reason why multi-parameter persistence is harder than single parameter persistence, because we can have pairs of elements which are not comparable, they're incomparable, and that really is the root of all the problems in multi-parameter persistence. So if we think about the decomposition theorem, that said that we can decompose our single parameter persistence modules into a series of intervals. Now, if we think about the analog of an interval in R to the n, we're going to generalize the definition of an interval of R using this convexity definition. So we say that an interval on the real line, we say a subset of the real line is an interval if, given any two elements of that interval, everything sandwiched in between those two elements is also contained in that interval. Now, if we use this same definition for the partially ordered set R to the n, we give rise to weird-looking subsets of R to the n, and these are known as intervals, and you can immediately see how these intervals are more complicated than the single parameter cousins. To define an interval of R, we just need to know the birth point and the death point, whereas in R to the n, these intervals are a lot more complicated. We can't just define a birth point and a death point, rather we just have this weird convex region of the plane. And when I say convex, I mean convex with respect to this partial order. So if you have any two elements lying in the interval, then the line between them will also lie in the interval.
So is it fair to say it's sort of convex when you're only looking at line segments with positive slope?
Yeah, exactly, precisely. It turns out that it is going to be convenient to think about this post set as a category, a thin category. And by thin category, I mean the objects of this category R to the n are just going to be the elements of the set R to the n, and there's going to be a morphism between A and B if and only if A is less than or equal to B. So we can define a multi-parameter persistence module then to be an element of the functor category of functors from this thin category R to the n to vector spaces. So what this is saying is we have a vector space living above each element of R to the n, and then between comparable elements we have a linear map. And if we use this definition, then we can phrase a morphism of these modules to be a natural transformation of these functors. So now just to give a concrete example of a multi-parameter persistence module, if you recall the interval from the previous slide, we can define a simple module from this interval where we take a one-dimensional vector space to live above every element of our interval, and then the morphisms living inside the interval are going to be isomorphisms, and the morphisms which start inside the interval and fall outside are going to be the zero map, and if you start outside and fall inside, then you're going to be the zero map as well. So not all multi-parameter persistence modules look like these interval decomposable modules, but they're a nice collection of examples to use in this talk, because I can illustrate them just by shading some region of the plane. And so if I've shaded some region of the plane, you should just assume that these morphisms are going to be isomorphisms within this shaded region. So I should emphasize now that the results of this talk are not restricted to interval decomposable modules, but all of my examples are going to be given as these interval decomposables because they're easy to present quickly. So a specific type of interval decomposable module is a free module, and these free modules are useful because they serve as building blocks to build up more complicated modules. So in order to define a free module, all you need to give me is a graded set X, and then I simply take the interval which is just the upset of this collection of this grade, and the resulting module just consists of a series of infinite cones expanding out into the positive direction away from these grades. So in the one parameter case, a free module just looks like infinitely long bars starting at various grades corresponding to the grades of this graded set. And in the plane, free modules just look like these cones extending out to infinity on the collection of points. And these free modules are free in the sense of like a free group, in the sense that if you give a morphism of this graded set to a module, that will then induce a morphism from the free module on this graded set to the image. Okay, so I said you could build up more complicated modules using these free modules, and we do so via presentations. So here I've sketched below a one-parameter persistence module, and I'm going to show how you can build this one-parameter persistence module using free modules. So our free modules in the one-parameter setting are just our infinite bars extending rightwards from a given graded set. So in order to define the presentation, I first need to give a free module which surjects onto my module M. So for example here, I just need 3 generators in order to surject onto these 3 bars of this module M. And then I want to quotient by the image of a free module R. So if I look where these bars have died, well then I can pull them back and take a free module on these grades and realize this module here M as the co-kernel of this map of free modules. And so really here what I've done, if you're more familiar with kind of rings and module theory, is I've just taken a free resolution of this graded module. And the decomposition theorem is really saying that every graded module over R which has this barcode decomposition then has a free resolution where you take a generator for each of the birth points and then a depth for each of the depth points of my barcode. Now the reason why I'm introducing this seemingly complicated free resolution of single parameter persistence is because it naturally generalizes to multi-parameter persistence modules. So if I revive my interval from before, I can surject onto this interval with a free module with 2 generators, and then the kernel of this map can be surjected onto with this free module of 5 generators. Now immediately we see a feature of these multi-parameter modules which didn't occur in single parameter persistence modules. In single parameter modules, all of my red points were the depths of my bars, whereas here you can have these relations which aren't inducing the death of generators, rather they're just identifying generators. So that's something which is a little bit different between multi-parameter persistence and single parameter persistence, and kind of points to the more complicated nature of these objects. So whilst I wasn't restricting my results to apply to interval modules, I am going to have to restrict my results to apply to this subclass of multi-parameter modules, which I'm going to describe as finitely presented. And so finitely presented modules are simply modules which have a finite presentation, those which are the co-kernel of two finitely generated free modules. So in this particular example, we could have a generating set A and B, and a kernel of this map consisting of these complicated elements, and this would give rise to this interval.
Can I ask a question?
Yeah.
Is it correct to say that if I take a finite two-dimensional filtration of finite simplicial complexes, and then I apply homology, that I always get a finitely presented two-dimensional persistence?
So if you're taking this, so if you have a function attached to a finite simplicial complex and take the sublevel set filtration, you will always give rise to a finitely presented module. Exactly.
Thanks.
Yeah, so this restriction is not too restrictive, because if we are working with a finite data set or a finite simplicial complex, and we look at the sublevel set persistent homology, then this will give rise to one of these objects. The analog of the birth and death points of bars in single parameter persistence are the so-called multi-parameter Betti numbers, which are the grades of the generators in a free resolution of our object. So Hilbert's syzygy theorem says that if you have a finitely generated Rn graded module, then you can take a free resolution of length at most n+1. So in the one parameter case, this said that we could take a resolution of length 2, which just consisted of births and deaths. And then the multi-parameter case is slightly more complicated, because not only do we have generators and relations, we also have relations between relations, and so on and so on and so on as we increase n. Now I'm introducing these objects because the locations of these generators are going to be important in our proofs later on. But you should really just think of these as the natural generalization of the endpoints of the bars of the barcode. And it just so happens that you can pick these resolutions in a minimal way, so that there's a minimal number of generators at each step. So I could have chosen a silly resolution where I introduced a generator and then I just killed it immediately in the next step. But that would be a silly thing to do, and I'm not going to mark those points, and I'm going to be marking the points of minimal generators. So one approach to analyze multi-parameter persistence modules is to try and leverage all of the information we know about one-parameter persistence modules. And so there's a nice idea of Mike Lesnick and Matthew Wright to look at all of the one-dimensional slices of a multi-parameter persistence module. So if we embed R in R to the n as a line, here I've drawn in purple, then if we look at the multi-parameter module restricted to this line, which I'm going to denote by this m to the l, well then we have a one-parameter persistence module living along this line, which will have a barcode decomposition, because it's just a one-parameter persistence module. And if we collect up all of the barcodes associated to all of the positively sloped lines through my module, I'm going to call that the fibered barcode of the multi-parameter persistence module. And so Matthew Wright and Mike Lesnick have some nice software with which you can explore this object on a two-parameter persistence module. It's called Rivet, and it's some nice software which allows you to explore this barcode in real time. So it turns out that this fibered barcode and the multi-parameter Betti numbers, which I introduced on the slide previously, are quite intimately related. The fibered barcode doesn't determine the Betti numbers, and the Betti numbers don't determine the barcode, but we can actually deduce information and flick between the two and deduce deduce information about the location of these Betty numbers from the locations of these bars in the fiber barcode and vice versa. And the way we do this is through these push functions which collapse r to the n onto these lines. So whilst the definition is maybe unclear, this is more easily seen with just an animation. If we have these multi-parameter Betty numbers living in this multi-parameter module, well, we can collapse them all to this line by extending them along the shortest line, which is increasing in the post set until they hit this line which we're probing of our module. And the reason why this is important is because if we then look at if we can induce a free resolution of our one parameter module from the free resolution of our multi-parameter module. So using the location of the multi-parameter Betty numbers, we can induce a free resolution of our single parameter persistence module. So for example here, if we had our barcode which was giving birth to one bar along this line, when we pushed our multi-parameter Betty numbers to this line, we induced a free resolution of this one parameter module where we gave birth to a single bar which was killed by a single relation. Now this resolution here was really inefficient because in various places I introduced a generator which was then killed immediately, or I introduced a relation which was killed immediately. So this resolution won't necessarily be minimal, but it does give me a resolution, and it allows me to pass between this fibered barcode and the locations of these multi-parameter Betty numbers. Okay, so the
question
first
is it correct to say that some of those ideas are what Rivet is doing behind the scenes?
Yes, exactly. Yes, so the first distance which I'm going to consider on these multi-parameter modules is the interleaving distance, which Lesnick generalized from one parameter modules to multi-parameter modules in his PhD dissertation. So the idea is completely analogous to the one parameter setting, where we're looking for morphisms between m and the shifted version of n, and between n and the shifted version of m, such that if you go from m to n and back again, it's as if you stayed in m. And similarly, if you go from n to m and back again, it was as if you stayed in n. So these interleavings are trying to knit together two modules, and the smaller that you have to translate your module when you knit them together, the closer together these two modules are. So really this two-dimensional picture is trying to encapsulate a three-dimensional phenomenon. So if we have two parameter modules, m and n, then when we knit them together, we're really trying to knit together two planes. And so this is a very complicated object with very complicated functions f and g knitting them together. So it won't be a surprise that computing this interleaving distance is a very hard thing to do. However, the interleaving distance has very nice theoretical properties in the sense that it's stable in a sensible suitable to a sensible definition of stability, and it's also very discriminative in the sense that two modules are zero interleaved if and only if they are isomorphic. So this interleaving distance really is the nicest distance we can consider on multi-parameter modules. The only downside is that it's very hard to compute. So in contrast, we can also consider this matching distance, which was defined by Seri and collaborators, which is again trying to leverage all the information we know about one parameter submodules of the multi-parameter module. So the matching distance is going to be defined on the fibered barcode, and what we're going to do is we're going to look at all of the lines through our multi-parameter modules and then just compare the barcodes along these lines. And we're going to say that the matching distance between the two modules is the maximum bottleneck distance between the barcodes as you vary over all of these positively sloped lines. Now there's a slight technicality which I'm not going to explain, because we actually have to weight these bottleneck distances by some weighting function, which gives slope 1 lines weighting 1, and the more shallow and the more steep your lines are, this weighting tends to 0. But this is a slight technicality, and it's just constructed in order that this matching distance is stable. So just a quick summary slide comparing these two metrics. We said that interleaving distance was theoretically well behaved in the sense that it's complete. So two modules are at distance 0 if and only if they're isomorphic. They're essentially the same module. It's stable and universal. So it's not only stable, but it is the most discriminative stable metric. So if you give me any other metric on multi-parameter modules which is stable, then it's actually going to have to be smaller than this interleaving distance. But the downside of this interleaving distance is that it's very complicated and it's in fact NP hard to compute and approximate, which was a result shown by Bjerkavik and collaborators. And it's NP hard to compute and approximate even in the 2-parameter setting and even for interval decomposable modules. So if we're interested in applications of multi-parameter persistence, there's no hope of using this interleaving distance because it's just too hard to compute. In contrast, this matching distance, which is really leveraging everything we know about the 1-parameter submodules of our multi-parameter modules, it has the downside that it's incomplete in the sense you can have two non-isomorphic modules which have 0 matching distance. But the good news is that it's stable and it's also computable, at least in the case n equals 2. So Kerber and collaborators showed that there's a polynomial time algorithm to compute exactly the matching distance between two 2-parameter multi-parameter persistence modules. And so if we're interested in applications, this matching distance is more appropriate. The only downside is that we don't have this nice theoretical guarantee that we had in the interleaving distance case. So the idea of this work is to try and recover a nice theoretical guarantee on the matching distance in comparison to this interleaving distance. So our main result says that if you give me a multi-parameter persistence module M and we look in a suitable local neighbourhood of M, then if you pick any module in this neighbourhood, well then the matching distance is in fact bounded below by some constant times the interleaving distance. And so we call this a local equivalence of metrics. Now I haven't told you yet how I define this local neighbourhood around M, but this is just intuitively what our result is. And so the nice thing about this result is that it says that locally around M, the fibered barcode is a complete invariant because the matching distance is just defined on the fibered barcode and the interleaving distance is complete. We know that if you look in the neighbourhood of M, this small neighbourhood of M, then M is the only module which has the same fibered barcode as M. So the fibered barcode is a complete invariant in a local neighbourhood of M. And we can also show that this local equivalence result induces a global equivalence result for intrinsic metrics. So if rather than just considering metrics between points in our space, we consider paths between modules, then we can show that the induced metrics of the matching distance and interleaving distance are in fact globally equivalent. And we do this by leveraging our local result and extending it to a global result when we're integrating our distance along paths. If you're not familiar with the terms in this statement, I'm going to explain it more later, so don't worry. So I just wanted to also state this example, which exhibits the incompleteness of the matching distance. It shows that the matching distance really is not a complete invariant for multi-parameter persistence modules. So here I've sketched two 2-parameter modules N and O, which are both interval decomposable. And if we think about the fibered barcode of these two objects, well, if we take a line which slices the support of this module, we're going to give rise to 2 bars. And these 2 bars are always going to have the same endpoint no matter how we move this line around. So one of the bars is going to correspond to one interval and the other bar is going to correspond to the other interval. And just by the way we've constructed this example, these bars will have the same endpoints, and so the fibered barcode is not going to be able to distinguish these two modules. And so this example shows that our local equivalence result is really the best we can hope for, because there's examples where the matching distance is not complete, and it's not going to be bounded by a constant of the interleaving distance, because the matching distance here is 0 and the interleaving distance is non-zero. The really local equivalence is the best we can hope for, and that's what we attain. So next I want to give a rough idea of how the proof of this statement goes. So I have to build up some machinery in order to give you an idea of how this proof goes, and the first thing I have to define are these grid functions. So a grid function really should be thought of as a lattice in R to the n. So here I've sketched two examples of these grids. One, a two-parameter grid, which is given by these blue points in the plane. And then associated to this two-parameter grid, I'm going to have this collection of hyperplanes, which I'm going to call grid sub G, which is going to be all of the lines which are axis aligned and passing through this grid. And similarly, if I give for a three-dimensional example, then if you imagine these points as a lattice in R3, then we also have all of these axis-aligned hyperplanes passing through these lattice points. And the reason why these grids are important is, if you remember the push function before, that this push function slid these multi-parameter Betti numbers along the axes in order to collapse R to the n to a line. And so really what I'm trying to capture here is the lines along which the multi-parameter Betti numbers might slide when we use this push function. And similarly, in the three-dimensional case, if you have a Betti number and a push function is going to push it along one of these hyperplanes in order to collapse it onto the line. So my result was a local result, and I gave you this little constant associated to my module, which I denoted C sub n. And the way I generate this constant is by considering the grid and looking at the minimal separation between the coordinates of the Betti numbers in this grid. So if I'm given a finitely presented multi-parameter persistence module, well then, because it's finitely presented, I know that I can place a finite lattice in R to the n such that I hit all of my multi-parameter Betti numbers. And then if I look at the controlling constant of this grid, this will give rise to a controlling constant of a module, which is well defined because these multi-parameter Betti numbers are well defined. And so yes, as I said before, this grid is important because this is really where our Betti numbers are going to slide when we're looking at the push function and trying to compare the locations of the multi-parameter Betti numbers to the endpoints of the bars in our fibered barcode. So I'm now going to give a kind of a rough sketch of how the proof of our result works. So we're going to start with two modules, and we're going to assume that they're interleaved, and the interleaving is close in comparison to the controlling constant of one of our modules. And now I claim that we can slightly modify our module n, and we can move these multi-parameter Betti numbers around so that they then lie on the same grid as m. So how do we do this? Well, if we imagine our fibered barcode passing through our two modules, well, because we know that their matching distance is small, we know it's bounded by their interleaving distance, then we know that any unmatched bar is going to be very small. And so if we have a generator which is lying far away from our grid, well, then we know it's going to be an unmatched bar because it can't be matched to a bar of m. Because if we're lying far away from the grid, then we lie far away from the endpoints of the bars of m, because if we imagine pushing our multi-parameter Betti numbers along the lines of this grid, if we're far away from the grid, then none of our generators are going to be pushed near to this endpoint on the grid. And so we define a operation on these multi-parameter modules which collapses these small generators and and kills them. And so we bring the relation to the same grade as the generator, and we bring the second order relation to the same order as the relation. And this causes these multiparameter Betti numbers to cancel out. And this, the cost of performing this operation is going to be some constant multiple of the matching distance, because the distance between the grades of these generators and relations is going to be small in the matching distance. Then similarly, we can also move these multi-parameter Betti numbers if they lie close to the grid. So it turns out if our multi-parameter Betti numbers are inducing long bars in our barcode, in our fibered barcode, they must be matched to bars in the fibered barcode of M. And so we can deduce that they must lie close to this grid. And we define something called a merge function, which pulls all of the multi-parameter Betti numbers which lie close to the grid to end up lying on the grid. So for example, here, if we look at this relation and the second order relation, they both lie close to this part of the grid, and our merge function collapses these generators of the free resolution to lie at the same grade and cancel each other out. So because I'm giving a very kind of a top-down view of this proof, in fact, what I've told you is a lot more simple than how it plays out in practice. And in fact, we have to perform a succession of these simplification and merges. The first two operations are used to bring the generators to the grid, and the second two operations are used to bring the relations to the grid. And after we do that, we can deduce that in fact all of the multi-parameter Betti numbers lie on the grid. So at the cost of 2 plus 2 plus 10 plus 20 times d0 in the interleaving distance, we can modify our module so that they end up having the same grid. Now the nice thing about this grid is we know how the modules behave if we stay within the same cell of one of these grids, because all of the morphisms within the same cell are isomorphisms. Because we don't pass the grade of any generator or relation, the maps of vector spaces here all have to be isomorphisms. And so if we know that M and M tilde have a small interleaving distance, well, we can invert these interleaving morphisms and in fact deduce that M tilde and M are in fact isomorphic. And so what we have done is we've moved M by some constant multiple of the matching distance and hit a module which is isomorphic to M. And using this, we deduce that the matching distance and interleaving distance must have this extra relationship when we're looking in a local neighborhood. Okay, so I spoke also about how this local equivalence result extends to a global equivalence result of modules when we think about paths between persistence modules.
Oliver, could I ask a question?
Yep.
So I'm guessing, is it correct to say that you don't think the constant 34 is sharp? And do you have any guesses on like what might a sharp constant be? Or for that example that you gave of N and O, you know, like do you, off the top of your head, do you know what constant you could take on that much simpler example of N and O?
So on that simple example, let me go back to that example. Here we go. So here, if we think about the controlling constant of n, it was taken to be the minimal distance between the Betti numbers. And so if we look in the local neighborhood of n, O will not lie in this local neighborhood because the interleaving distance between n and O is this distance between the Betti numbers. So we exclude this case by looking in a local neighborhood of n.
Right.
Can I also ask a question on a related note while we're still here? Yeah, I was wondering where the number 34 comes from. I see that it's 20 plus 10 plus 2 plus 2. But then where do these numbers come from? If you can just give us some intuition behind them.
Okay, yes. So to start with, if we assume that M and N are have distance d0, then the unmatched bars are going to be of length 2d0. So in order to collapse them, I pay a penalty of 2d0. And then, but then it's kind of an almost inductive proof. And so when I pay a cost of 2d0, this m dash is now 3d0 away from m. And so as I'm increasing this distance, that is why these kind of the distance I have to merge and simplify is increasing. I mean, I will put something on the archive soon, and you can look at the nitty-gritty details. But essentially, you should think that these first two are bringing the generators, controlling the generators by, first of all, killing the ones which generate small bars, and then bringing them to the grid. And then these guys are sorting out the relations. And because we've paid a price of 4d0 here, we're having to then increase how much we're moving our generators in our successive steps. I'm not sure that's satisfactory because it's quite a technical proof, and I don't really have any kind of top level kind of intuition as to why you'd expect 34.
Yeah, no problem. I'll check the archive when it's there. Thanks.
Okay, perfect. Okay. So yes, we want to induce a global equivalence from our local equivalence result. And in order to do so, we have to think about paths between persistence modules. So in the one parameter setting, we can think about a path between two barcodes by smoothly changing the location of the endpoints. So here, for example, if we have a matching between m and n, where we match these two long bars, these two medium bars, and then we collapse this small bar to 0, we can think about a path between these two modules by continuously changing the endpoints of these bars. Or if you prefer, if you think about the persistence diagram, you can just think about moving points of the persistence diagram to create a path of barcodes which is continuous in the bottleneck distance. Now this notion of moving endpoints actually generalizes to multi-parameter modules. So Mike Lesnick showed in his thesis that you can actually characterize interleavings by presentations. So we can say that module M and N are epsilon interleaved if and only if they have this pair of compatible presentations where they have the same generating sets and the same relations, just they have been shifted around in their grading by epsilon. Now this presentation is not necessarily minimal, but it does mean that we can deduce that the space of multi-parameter persistence modules is a path metric space because we can define a smoothly varying path between these two presentations, which realizes that if you have an epsilon interleaving between m and n, there's an epsilon length path in the interleaving distance between m and n. So just as we moved the endpoints of the barcode in the single parameter case, we can move around the multi-parameter Betti numbers and find a path between two modules. Now, given paths in the space of persistence modules, or more generally any metric space, you can define the length of these paths with respect to some metric, with respect to any metric d. So to define the length of the path, you simply look over all partitions of our interval, and then you just do a finite approximation of the length of the path by just summing up the kind of small little jumps along our path. And if you take supremum over all partitions, this gives a well-defined notion of length for these paths. And so using this notion of length, we can induce another metric on our space of persistence modules, which we're going to call the intrinsic matching distance. So if you're given a metric on space of multi-parameter modules, and then you just look at it integrated over all paths, or the shortest path, then the resulting distance is known as an intrinsic metric because you have paths which realize that distance between the modules. And so saying that the multiparameter modules equipped with the interleaving distance as a path metric space is just saying that this intrinsic metric is the same as the original metric. So just a quick sketch of how this global equivalence of metrics proof goes. Well, we have a local equivalence result, which means that if we're given any path in our space of multiparameter persistence modules, we have some local neighbourhood where our lower bound holds. And so we can find some partition which covers our path using compactness. And then if we just take a finer partition which jumps between these local neighbourhoods within which our inequality holds locally, then we in fact induce a global result. So I guess I can summarize in conclusion, the main points to take away from this talk is that the fibered barcode is in fact a locally complete invariant for finitely presented multiparameter persistence modules. So although globally it's incomplete, if you're looking locally, it's a complete invariant, and it does just as well as the interleaving distance, just up to some constant factor. And so a nice consequence of this is that if you have another invariant which is faithful to the fibered barcode, you have some other representation of the fibered barcode, then this is also going to be locally complete, which will motivate using these invariants in any applied situation, because we know that there's some theoretical guarantee saying that they discriminate between different modules well, at least locally. So then more from a applied standpoint, if there was any way we could compute or approximate this intrinsic matching distance which we've defined, if there was a nice way to find paths between modules, then we might be able to approximate the interleaving distance, which is known to be hard to compute. And finally, here I just talked about multiparameter persistence modules, but this is actually a very broad class of a very broad category, and you can in fact embed other topological data structures within multiparameter persistence modules. So for example, if you're familiar with interlevel set persistence modules, these naturally embed in two-parameter persistence modules. And so if you want to know anything about Reeb graphs, the persistence modules associated to Reeb graphs also embed in two-parameter persistence modules. And so this general result for finitely presented multiparameter modules actually induces, as corollaries, some similar results for these other data structures when you think about them as types of multiparameter persistence modules. So I just wanted to also highlight some related work. So Matthew Carrière and Steve Udo look at a similar question in the restricted setting of Reeb graphs, where again they look at a hard to compute metric and an easy to compute metric, and they showed that these two metrics are locally equivalent. Havard Bjerkovic looks at a couple of metrics specifically on the class of interval decomposable modules and shows relationships between these metrics. And then, as mentioned before, Michael Kerber and collaborators have shown that this matching distance is in fact computable in polynomial time, and so is a good candidate if we want to look at applications of multiparameter persistence. That's all I have to say, but I'm very happy to answer any questions.
Fantastic. So as a sort of tradition, before we get to questions, go ahead and unmute yourselves, and then we'll clap, and then we'll mute ourselves again before questions. So let's give it a shot. Great. So go ahead and mute yourselves, but please do unmute yourself to ask a question.
Probably.
Go ahead, Claudia.
Oh, thank you. Very nice talk, Oliver. I have questions. Maybe you have explained that, but I missed that. How do you define the constant that you use, the constant for the module M that you use in your inequality?
Okay. So if we have one of these finite grids, we look at the minimal separation between the coordinates in this lattice. So in this particular example, this distance is the smallest distance between these two points in my lattice, and really I'm thinking about this lattice associated to the Betti numbers of a multiparameter module. So yeah, the constant is the smallest distance between any of the coordinate values of any of the multiparameter Betti numbers. And we use that as our constant really because we want to know the size, like within these cells, we just have isomorphisms, and so we can control the behavior within these cells, and we know how small the smallest, the cell which we've decomposed Rn into. We want to know the smallest kind of size of one of the lengths of these cells. I guess I should also say in analogy, in the one parameter case, it would be the smallest distance between endpoints of the barcodes.
Other questions? Oliver, what is interlevel set persistence? Is that a special case of zigzag persistence?
Yes, so you take your poset to be the intervals, the connected intervals of R.
Great.
So it's kind of a continuous a version of zigzag persistence. Yeah.
Other questions? Well, if not, before I end the recording, let me just thank everybody again for joining. We'll meet again a week from today, actually a half hour earlier, and the speaker will be Gugan Thulp, who's on the call right now. So thanks again, Oliver, for the fantastic talk.